Hello students, in this lecture we are going to study the difference between the real cycles, that is actual cycles, and the fuel air cycle, and moreover we are going to study the various factors that are leading to various losses in the actual cycle. Now till now we have studied air standard cycle, then we came to fuel air cycles, and now we are discussing the real cycles, that is actual engine cycle. So now when we are studying the actual engine cycle, then we will be studying the various factors which are leading to various losses in the actual cycle which were not considered in air standard cycle. Now this table shows that actual cycle efficiency is much lower than the air standard efficiency due to various losses that are occurring in the actual engine operation. And this shows that for the compression ratio of 7:1, both the cycles have been compared. The air standard cycle shows the efficiency of 55%, whereas the actual engine cycle is just around the half of the thermal efficiency which was there for the air standard cycle. So now you can understand the great gap between the air standard cycle's efficiency and that of actual engine cycle. Now the major losses that are creeping in the actual cycles are due to variation of specific heats with temperature, dissociation of combustion products, progressive combustion, incomplete combustion of fuel, heat transfer into the walls of the combustion chamber, blowdown at the end of exhaust process, and the gas exchange process. See, an estimate of these losses can be made from the past experience and some simple tests on the engines, and these estimates can be used in evaluating an engine. If we subtract losses due to variable specific heat and dissociation from the air standard cycle, we get fuel air cycle analysis. And if we further subtract other losses from fuel air cycle analysis, we can very closely approximate the actual cycle. This figure is showing the difference between the ideal Otto cycle and the actual cycle. The simplest one is the air standard cycle, in which all the assumptions were simplified. We have not taken into the consideration the disintegration of the products of combustion or the working substance as a whole. Even the constants like Cp, Cv, and gamma, they were assumed to be constant throughout the range of operation. There was no dissociation of elements as such. Now, when some of the things like variable specific heat was considered to vary along with the temperature that were encountered in the range of operation, when we consider the dissociation, this deviated bit from the air standard cycle, and this came to known as fuel air cycle. Now further in fuel air cycle, we took into account for the combustion losses, time losses, heat losses, blowdown losses, and the cycle which resulted was the actual air cycle. Now after that, we also took into account the actual work losses, and that gave us the useful work which is used to drive the prime mover. The actual cycles for IC engines differ from air standard cycle in many respects, and these differences are basically due to these factors. The working substance being a mixture of air and fuel vapor, or finely atomized liquid fuel in the air combined with the products of combustion. the change in the chemical composition of the working substance, the variation of specific heats with temperature, the change in the composition, temperature and actual amount of fresh charge because of the residual gases. The progressive combustion rather than the instantaneous combustion. The heat transfer to and from the working medium. The substantial exhaust blowdown loss, that is loss of work on the expansion stroke due to early opening of the exhaust valve. Gas leakage, fluid friction, etc. in actual engines. Now, point first to fourth being related to fuel air cycles have already been discussed in previous lecture, that is the lecture pertaining to fuel air cycles. Now the remaining points, that is point 5th to 8th, are in fact responsible for the difference between fuel air cycles and actual cycles. Now most of these factors, they tend to decrease the thermal efficiency as well as power output of the actual engines. On the other hand, the analysis of cycles while taking these factors into account clearly indicates that the estimated thermal efficiencies are not very different from those of actual cycle. Now the major losses that are found in actual cycle are time loss factor, heat loss factor, exhaust blowdown factor. Now the time loss factor is basically the loss due to the time required for mixing of fuel and air and also for combustion. Heat loss factor is basically due to the loss of heat from gases to cylinder walls. Exhaust blowdown results due to the loss of work on expansion stroke due to early opening of the exhaust valve. Now, time loss factor. In air standard cycle, the heat addition is assumed to be at instantaneous process, whereas in an actual cycle, it is over a definite period of time. The time required for the combustion is such that under all circumstances, some change in volume takes place while it is in progress. The crankshaft usually turns about 30 to 40 degrees between the initiation of the spark and the end of combustion. There will be time loss during this period and is called time loss factor. The results of the finite time of combustion is that the peak pressure will not occur when the volume is minimum, that is when the piston is at top dead center, but will occur sometime after top dead center. The pressure therefore rises in the first part of the working stroke from B to C as shown in figure. The point 3 is basically showing you the state of gas had the combustion been instantaneously, and an additional amount of work equal to the area shown as would have been done. This loss of work reduces the efficiency and is called time loss due to progressive combustion, or simply the time losses. The time taken for the combustion depends upon the flame velocity, which in turn depends upon the type of fuel and the fuel air ratio, and also on the shape and size of the combustion chamber. Moreover, the distance from the point of ignition to the opposite side of the combustion space also plays an important role. In order that peak pressure does not reach too late in the expansion stroke, the time at which combustion starts is changed by varying the spark timing or spark advance. Now this figure basically shows the effect of spark timing on PV diagram. Now with the spark at top dead center, means no advance, the peak pressure is low due to expansion of gases. This figure basically shows the effect of spark timing on PV diagram. Here the spark is advanced by 35 degree. So as the spark is advanced to achieve the complete combustion close to top dead center, therefore it requires additional work to compress the burning gas. This represents basically direct loss. In either case, that is with or without spark advance, the work area is less and the power output and efficiency are lowered. Therefore, a moderate or optimum spark advance is the best compromise, resulting in the minimum losses on both the compression and expansion stroke. So this figure basically gives us the optimum value of the spark advance, which lies between 15 to 20 degree, and that basically results in minimum losses on both compression and expansion stroke. So this table basically compares the engine performance for various ignition timings for the compression ratio 6. Now here we are having the various performance parameters value for the compression ratio 6 for the different ignition advances. So the first row shows for the fuel cycle the ignition advance is 0 and the maximum cycle pressure is 44 bar and MEP is 10.2 bar and the efficiency is 32.2%. Now for the actual cycle we are having all these values for 0 degree ignition advance, 17 degree ignition advance and 35 degree ignition advance, and we found that maximum efficiency as well as the ratio of actual efficiency and fuel cycle efficiency is found in case of the advance of 17 degree. As you know that the area within the geometrical figure on the PV diagram will not only represent the work output, or you can say the power generated by the engine, but also this area for the given specific volume will basically give us the magnitude of indicated mean effective pressure, which is an important performance parameter for an IC engine. So as shown in the figure, fuel air cycle is having the largest area on PV diagram, henceforth it is having the highest IMEP, that is indicated mean effective pressure, as well as highest efficiency. Now for the actual cycles shown for the different advances, that is ignition advances of 0 degree, 17 degree and 35 degree, we are having the maximum area for these three for the 17 degree. So IMEP for these three advances will be maximum for the 17 degree ignition advance, henceforth efficiency will also be maximum for this value of ignition advance. As we have seen, when the ignition advance is increased beyond a certain limit, it results basically significant reduction in the value of indicated mean effective pressure, that is IMEP, and the consequent loss in power. However, sometimes a deliberate spark retardation from optimum may be necessary in actual practice in order to avoid knocking and to simultaneously reduce the exhaust emissions of hydrocarbons and carbon monoxide. At full throttle, with the fuel air ratio corresponding to maximum power and the optimum ignition advance, the time losses may account for a drop in efficiency of about 5%. That is, fuel air cycle efficiency is reduced by about 2%. These losses are higher when mixture is richer or leaner, when the ignition advance is not optimum, and also at part throttle operations the losses are higher. It's impossible to obtain a perfect homogeneous mixture with fuel vapor and air, since residual gases from previous cycle are present in the clearance volume of the cylinder. Further, only very limited time is available between the mixture preparation and ignition. Under these circumstances, it's possible that a pocket of excess oxygen is present in one part of the cylinder and a pocket of excess fuel in another part. Therefore, some fuel does not burn or burns partially, leading to the formation of carbon monoxide, and the unused O2 appears in the exhaust. This figure basically shows the composition of exhaust gases for various fuel air ratios. As one can see that CO2 is maximum at stoichiometric air fuel ratio, whereas the formation of CO increases with the increase in fuel air ratio by weight, and that of O2 decreases with the fuel air ratio beyond the chemically correct mixture, that is stoichiometric air fuel ratio. If we analyze energy release data, we come to know that only about 95% of energy is released with the stoichiometric fuel air ratio. Energy release in actual engine is about 90% of fuel energy input. It should be noted that it is necessary to use a lean mixture to eliminate wastage of fuel, while a rich mixture is used to utilize all the oxygen. Slightly leaner mixture will give maximum efficiency, but too lean a mixture will burn slowly, increasing the time losses, or will not burn at all, causing total wastage of fuel. In a rich mixture, a part of the fuel will not get necessary oxygen and will be completely lost. The flame speed in mixtures more than 10% richer is low, thereby increasing the time losses and lowering the efficiency. Even if this unused fuel and oxygen eventually combine during exhaust stroke and burn, the energy which is released at such a late stage cannot be utilized. Imperfect mixing of fuel and air may give different fuel air ratios during suction stroke, or certain cylinders in a multi-cylinder engine may get continuously leaner mixture than others. During the combustion process and the subsequent expansion stroke, the heat flows from the cylinder gases through the cylinder walls and cylinder head into the jacket or cooling fins. Some heat enters the piston head and flows through the piston rings into the cylinder wall, or is carried away by the engine lubricating oil, which splashes on the underside of the piston. The heat loss with the other losses is shown on this PV diagram. Heat loss during combustion will naturally have the maximum effect on the cycle efficiency, while heat loss just before the end of expansion stroke can have very little effect because of its contribution to the useful work is very little. The heat loss during the combustion does not represent a complete loss, because even under ideal conditions for air standard cycle, only a part of this heat could be converted into work, that is equal to Q into thermal efficiency, and the rest would be rejected during the exhaust stroke. About 15% of the total heat is lost during combustion and expansion. Of this, however, much is lost so late in the cycle to have contributed to useful work. If all the heat loss is recovered, only about 20% of it may appear as useful work. This figure basically is showing that percentage of time loss, heat loss and exhaust loss in a CFR, that is Cooperative Fuel Research Engine. The effect of heat loss during combustion is to reduce the maximum temperature, and therefore the specific heats are lower. It may be noted from the figure that I have shown you on the last slide that of the various losses, heat loss factor contributes around 12%. Exhaust gas blowdown. See, the actual exhaust process consists of two phases: blowdown and displacement. As one can see from the figure, that at the end of power stroke, when the exhaust valve opens and the cylinder pressure is much higher than the exhaust manifold pressure, which is typically at 1 atmosphere. So here P4 stands for the pressure inside the cylinder at the end of expansion stroke, whereas PE denotes the pressure in the exhaust manifold. So basically, the pressure at the end of expansion stroke is higher than the pressure in the exhaust manifold. So the cylinder gas flows out through the exhaust valve and the pressure drops to PE, that is, it drops to exhaust manifold pressure. Now, in the displacement, remaining gas is pushed out of the cylinder by the piston from BDC moving towards TDC, as shown in the figure. The cylinder pressure at the end of exhaust stroke is about 7 bar, depending on the compression ratio employed. If the exhaust valve is opened at the bottom dead center, the piston has to do work against high cylinder pressures during the early part of the exhaust stroke. If the exhaust valve is opened too early, a part of the expansion stroke is lost. The best compromise is to open the exhaust valve 40 to 70 degree before bottom dead center, thereby reducing the cylinder pressure to halfway, say for example 3.5 bar before the exhaust stroke begins. The difference of work done in expelling the exhaust gases and the work done by the fresh charge during the suction stroke is called the pumping work. Also, we can say that loss due to the gas exchange process, that is pumping loss, is due to the pumping gas from lower inlet pressure PI to higher exhaust pressure PE. The pumping loss increases at part throttle because throttling reduces the suction pressure. Pumping loss also increases with the speed. The gas exchange processes affect the volumetric efficiency of the engine. The performance of the engine to a great deal depends on the volumetric efficiency. The volumetric efficiency is an indication of the breathing ability of the engine, and it is basically defined as the ratio of the volume of air actually inducted at ambient condition to the swept volume. It may also be defined on the mass basis as the ratio of the actual mass of air drawn into the engine during a given period of time to the theoretically mass which should have been drawn in during that same period of time, based upon the total piston displacement of the engine and the temperature and pressure of the surrounding atmosphere. Now, this definition that we have discussed just now is applicable only to the natural aspirated engine. In the case of supercharged engine, the theoretical mass of air should be calculated at the condition of pressure and temperature prevailing at the intake manifold. The volumetric efficiency is affected by many variables like the density of the fresh charge, the exhaust gas in the clearance volume, the design of the intake and exhaust manifold, and the timing of intake and exhaust valves. The density of fresh charge. As the fresh charge arrives in the hot cylinder, heat is transferred to it from the hot chamber walls and the hot residual exhaust gases, raising its temperature. This results in a decrease in the mass of fresh charge admitted and a reduction in volumetric efficiency. The volumetric efficiency is increased by low temperatures, provided there are no heat transfer effects, and high pressure of the fresh charge, since density is thereby increased and more mass of charge can be inducted into a given volume. The exhaust gas in clearance volume. As the piston moves from top dead center to bottom dead center on the intake stroke, these products tend to expand and occupy a portion of the piston displacement greater than the clearance volume, thus reducing the space available to the incoming charge. Moreover, these exhaust products tend to raise the temperature of the fresh charge, thereby decreasing its density and further reducing volumetric efficiency. The design of intake and exhaust manifolds. The exhaust manifold should be so designed so as to enable the exhaust products to escape readily, while the intake manifold should be designed so as to bring in maximum possible fresh charge. This implies minimum restriction is offered to the fresh charge flowing into the cylinder as well as to the exhaust products being forced out. The timing of the intake and exhaust valves. Valve timing is regulation of the points in the cycle at which the valves are set to open and close. Since the valves require a finite period of time to open or close for a smooth operation, a slight lead time is necessary for proper opening and closing. The design of the valve's operating cam provides for a smooth transition from one position to the other, while the cam's setting determines the timing of the valve. The effect of intake valve timing diagram on the engine air capacity is indicated by its effect on the air inducted per cylinder per cycle, that is, mass of air taken into one cylinder during one suction stroke. Now this figure shows the representative intake valve timing for low speed engine. While the intake valve should open theoretically at top dead center, almost all SI engines employ an intake valve opening of few degrees before top dead center on the exhaust stroke. This is basically to ensure that valve will be fully open and the fresh charge starts to flow into the cylinder as soon as the piston reaches top dead center. Now, as shown, the intake valve start to open 10 degrees before top dead center. It may be noted that the intake valve closes 10 degrees after bottom dead center. As the piston descends on the intake stroke, the fresh charge is drawn in through the intake port and valve. When the piston reaches bottom dead center and starts to ascend on compression stroke, the inertia of the incoming fresh charge tends to cause it to continue to move into the cylinder. At low speed of the engine, the charge is moving into the cylinder relatively slowly and its inertia is relatively low. If the intake valve were to remain open much beyond bottom dead center, the upmoving piston on the compression stroke would tend to force some of the charge already in the cylinder back into the intake manifold, with consequent reduction in volumetric efficiency. Hence, the intake valve is closed relatively early after bottom dead center for a slow speed engine. High speed engines, however, bring the charge in through the intake manifold at greater speeds, and the charge has greater inertia. As the piston moves up on the compression stroke, there is a ram effect produced by the incoming mixture, which tends to pack more charge into the cylinder. In the high speed engine, therefore, the intake valve closing is delayed for a greater period of time after bottom dead center in order to take the advantage of this ram and induct the maximum quantity of charge. Now this is the valve timing diagram for a high speed engine. Here the opening of intake valve takes place 10 degrees before top dead center, but the intake valve closes 60 degrees after top dead center. For either a low speed or high speed engine operating in its range of speeds, there is some point at which the charge per cylinder per cycle becomes a maximum for a particular valve setting. If the revolutions of the low speed engine increases beyond this point, the intake valve in effect close too soon and the charge per cylinder per cycle is reduced. If the revolutions of the high-speed engine increases beyond this maximum, the flow may be choked due to fluid friction. These losses can become greater than the benefit of the ramp and the charge per cylinder per cycle falls off. The chosen intake valve setting for an engine operating over a range of speeds must necessarily be a compromise between the best setting for the low speed end of the range and the best setting for the high speed end. The timing of the exhaust valve also affects the volumetric efficiency. The exhaust valve usually opens before the piston reaches the bottom dead center on the expansion stroke. This basically reduces the work done by the expanding gases during the power stroke, but decreases the work necessary to expel the burned products during the exhaust stroke and results in an overall gain in output. During the exhaust stroke, the piston forces the burned gases out of the cylinder at high velocity. If the closing of the exhaust valve is delayed
Loss
beyond
due to rubbing friction. These losses are due to the friction between the piston and the cylinder valves.
The cylinder better by carrying
Friction
out
in various bearings and also the energy
gas
spent in
left
operating
the
the
clearance
auxiliary
volume
equipment such
and
as cooling
results
water pump,
in an
ignition
increased
system,
volumetric
fan, etc.
efficiency.
The piston
Consequently,
ring
the
friction
exhaust valve is
increases
often
rapidly
set
with
to
engine
close a
speed.
few degrees after top dead
It
center
also increases
on
to
the
a
exhaust
small
stroke
extent with increase in mean effective pressure.
It should be noted
The
that
bearing
it is
friction
quite
and the
possible for
auxiliary
both
friction
the
also
intake and
increase with
exhaust
engine speed.
valves to remain open.
The efficiency
or
of an
partially
engine
open
is maximum
the
at full
same
load
time.
and
This is
decreases
termed
at
as
part
valve
loads.
overlap.
It is because the percentage of direct heat loss, pumping loss,
The
and
overlap,
rubbing
of
loss
course, must not be
increase
excessive
at
enough to allow
part
the burnt
loads.
gases to be sucked into the intake manifold or the fresh charge to escape through the. Now, the approximate losses for a petrol engine of high compression ratio, say 8:1, using a chemically correct mixture, are given in this table as a percentage of fuel energy input. So we are having the readings of various losses as well as efficiency for full load as well as half load. So we can see that at full load and half load, losses due to variation of specific heats and chemical equilibrium, they remain same. Similarly, the burning time losses, incomplete combustion losses, and exhaust blowdown losses, they remain same. The variation occurs in rubbing friction loss. At full load, it is 3.2%, whereas at half load, it is 6.4%. So actual brake thermal efficiency at full load is 32.6%, whereas at half load is 26.3%. This is all for the actual cycles of IC engine. Thank you.